Hello everyone. So today we are going to talk about Prim's algorithm to find the minimum spanning tree. Already we have discussed the Kruskal method to find the minimum spanning tree. Now we will discuss the Prim's method and also will compare that how it is different from the Kruskal method. So let's start. Okay, so in the Prim's method, or you can say the Prim's algorithm, in this it has the property that the edges in the set A always form a single tree. In the previous method, in the Kruskal method, we have seen that while constructing our spanning tree, the minimum spanning tree, we are getting unconnected components. We are having the vertex, we are keep on picking the edges with the minimum weight and adding to our solution set. And with this procedure, we also uh, come across that the tree is not connected throughout the process. But in the Prim's method, when we uh, constructing our spanning tree, we will find that the tree that we are building, that we are constructing, will always be connected. Means all the vertex that we are choosing to construct our tree will always be connected throughout the process. Now this method is very similar to the Dishitra method for finding the shortest path or the shortest route. So in the next lecture we are going to talk about Dishitra method, and there you will realize that the Prim's method is very much similar to the Dishitra method. Okay, so now we'll see the strategy that how this method works. So in this method we need to select one vertex and we are calling as a root. In the Kruskal method, when we start, we need to sort the edges in the ascending order and then we pick the edge with the minimum weight. But in this, here you have to identify one vertex we are calling as a root as a starting point, and then branch out from the tree constructed so far. And from this vertex we keep on branching out. The tree means we keep on forming the tree by picking a edge at each iteration, and then we attach this edge to this vertex. Now which edge to select? It is working in the greedy approach, so we will pick the vertex and we will see what are the other vertex that is connected to this vertex, and the vertex which is connected with the minimum weight will be selected to be connected for our desired tree. Then add to the tree to the vertex associated with the edge. Okay, this already we have discussed. During the course of the algorithm, vertices are divided into three disjoint categories. So when we are following this procedure, we come across, uh, or you can say when we are following this procedure, we are actually dividing the entire sort of set of vertex into three categories, and we are calling this as a tree vertices, fringe vertices and unseen vertices. So the overall vertices which are given in the graph we have divided into three categories. Now tree vertices are the vertices which are already included in our solution tree. So when you have decided that the vertex to be chosen in our tree, then that vertex is a part of the tree vertices. Fringe vertices are the vertices which is still not a part of the tree, but it is actually very near to our selected vertex. So, or you can say the vertex which is actually have a path to the vertex which is already a part of tree are said to be a fringe vertices. So these are the adjacent to some vertex in the tree. Unseen vertices are all other vertices which are not included in the tree vertices and in the fringe vertices. So we will see that what are tree, fringe and unseen vertices in one diagram, or you can say in this figure, in this graph. We will try to understand that how we have categorized these three set of vertices. So as we have discussed that in order to start with the Prim's method, we need to choose one vertex as a starting vertex or as a root vertex. So here we have chosen, let's say A we have chosen to start. Now when we have chosen this, so this means this is already a part of a solution, so we are calling this as a tree vertex. And all the neighbors of this vertex, so the neighbors of this vertex is B, G and F. So you can say B, G and F are the neighbors of the vertex. When I say neighbors means there is a direct connection to these vertices. We have a edge that connects to these neighbors. So these three becomes the fringe vertices, means these vertices are already connected to our tree vertices, but we have not chosen these vertices in our solution. Now the next part is we have to select one vertex out of the fringe vertices to become a part of our solution, and this is decided by the greedy approach, means we will check that which among these fringe vertices has a minimum cost. So we have 2, 3 and 7, so the 2 is minimum, so we will take this vertex in our solution set. So this B is now a part of this tree vertices. Now we will also consider the neighbors of B in the fringe set. So now if you look at this, the neighbor of B is C. So now you can see along with this two, now we have one more vertex that is included in the fringe vertices set. Now we have to choose among these fringe vertices which vertices to become the part of tree vertices, and this can be done by looking to the cost of these edges. So we will select the minimum edge, means we will select the vertex with which have a edge with the minimum weight. So if you look at these three options, you will find that tree is having a minimum weight, so G is going to become a part of the tree vertices. So now we have A, B and G. Already we have decided to make our minimum spanning tree using these vertices. Now again, because we have selected the G, so we have to also consider the neighbors of G, that is I, H, A and B is already the part is already in the trees vertices set. So I and H is going to be included in the fringe vertices set. So we keep on moving in this way, and you may notice that here we have a direct path from A to F, that is the path A to F, which is having an edge with weight 7. But later you will find that now this path has been removed, because already we have find some another path that goes to F through I. So we keep on moving in this way, and this is how we will find. And finally when you stop, you will find that all the vertices must be included in the tree vertices. That means actually we are looking for a tree, means minimum spanning tree is a tree which contains all the vertex of the graph and that connects with the minimum weight edges. This is the purpose of minimum spanning tree. Now one thing to observe here, that while constructing our minimum spanning tree, so here you can see we have A, then we have AB, then we have ABG, then we have ABGI, and then we have this structure, and we will find that it will remain connected throughout the process. So like in the Kruskal method, if you remember, we are constructing our tree, but the tree may be disconnected at some point of time, but in the Prim's method it will remain connected. This is one difference between the Prim's and the Kruskal method. So now we will or we will discuss a formal algorithm of Prim's method. This is a formal algorithm. So if you want to implement as a program, you can just refer to this algorithm and you are able to implement the minimum spanning tree, or you are able to find the minimum spanning tree for any given graph. Now the name of this procedure is given as MST. You can say at minimum spanning tree by using a Prim's method, and we need to pass three parameters. One is the graph, other is the weight of the graph. So we need to provide the graph, that is a set of vertex and edges, and along with the weight, because if the weight is not given in the edges, then there is no need to find the minimum spanning tree. Then R is the vertex which you are choosing as a root, so you need to also pass this. When you pass the three parameters, then we need to do these three things initially. So this is called initialization. So initially what is required for each u, that is a part of vertex uh, vertex set of this graph. So or you can say for each vertex that is a part of this graph, do key u infinite. We are assigning every vertex the infinite value, and we are calling as a key value of this vertex as an infinite. Now key value is basically refers to the the cost that is required to move to the neighbor, to the predecessor, to the previous node. So initially we write as infinite, that means there is no path available to move to any of the neighbors, or there is no previous node of any of the vertex. So we are assigning that as infinite. And pi u is basically, you can say, this refers to the predecessor of any vertex or the previous node of any vertex. What does this mean? It means if I make this graph, let's say A, B, C. So if I am saying I am moving from C to C from B, then the predecessor of C is B. Means I am reaching to C from B. So if I say the predecessor of B is A, or if I say the predecessor of B is C, it makes a difference. If I say the predecessor of B is A, that means to reach to B I should follow A, means I can reach to B from A. If I say this pi of B equals to C, that means to reach to B I should follow this path from C to B. So the meaning of this is it will denote the predecessor, or you can say the previous node, that will help you to reach to the next node. So initially we are assuming that there is no predecessor node for any vertex, we are keeping as a nil. So this is called initialization. Then key of R. Now R is a vertex which we are assuming as a root vertex, or you can say the root node from where we have to start. Only this vertex is assigned value 0 and all is actually having infinite. Okay, then Q is a set that contains all the vertex. So Q is a set that contains all the vertex, and we need to remove the vertex from this Q set. And when so we keep on removing the vertex from the Q set, and when the vertex and when the Q becomes empty, we need to stop. So until the Q is not empty, we are keep on doing this process, and when the Q becomes empty, we will stop. And when you stop, you will find that your minimum spanning tree is already constructed. So what is required? So we need to remove the vertex from this Q set. And how we are removing? Extract min. Extract min is a procedure that will remove the vertex from the Q set. So extract min will actually extract the vertex with the minimum key value. Or you can say we have the Q set which consists of vertex. Let's say this is a graph given to us. We have A, B and C, and let's say we have the key value here is 2, here we have 1, here we have 9. So when I say extract min Q, that means out of all the vertex which is a set of this Q, I am looking for the vertex which have a minimum key value. These are the key value. So at this point of time we will get as B, because B is having a minimum key value. So we will call extract min on this set, and this will return one vertex with the minimum key value, and we are calling it as a U. For each V that is a belongs to adjoint of U. So adjoint refers to the neighbors. Neighbors means all the vertex which have a edge connected to any vertex. So what does it mean? For each vertex, so we have got this vertex from this set Q, and we will look to all the neighbors of this vertex which we have got from this set, and do if V is a if V belongs to Q. So if V is a part of Q, then WUB and key V. Now what does that mean? It means, so we will look to all the vertex V which is a neighbor of this vertex which we have extracted. And now if V is a part of Q, means the neighbor is a part of Q which is still existing in the set, and the path from U to V is less than the key value, then if this is identified, if you find that this path value is less than the key, then you are going to update the predecessor of this vertex. Now if this is not true, then we are not going to update this. This is actually means that you are able to find a new path which gives you the lesser cost than the previous one. So you are updating, you are saying that now my predecessor node is u, because this cost is less than the key value. Okay, so now we are saying that this is one vertex uv. Okay, and we have the key value of this, we have a key value of this, and also we have a weight of this. So let us take some imaginary values in order to understand this statement. Let's say the key value of u is 10, the key value of v is 9, and this weight is 2. Okay, so here this is not actually considered. We are looking for the key value of v and the wuv. This is called wuv. So if this value, if wuv is less than the key value of v, then you need to take this, means then only we will do this step. If this value is less than this value, then what we will do, we will say that the predecessor of v is u. That means in order to reach to v, we will follow from u, because this is the better path, this cost is uh, lesser, or is the best among all the available option. So the meaning of this is, here if this is true, that means we are saying in order to reach to v, we will follow from u, and also we will update the key of v is wuv, and because we have selected this path, then we will update this, and now this is not 9, this becomes 2. Okay, in contrast to this, let's say if we have the situation like this, u v, this is 10, this is 9, and this is, let's say, 12. Now in this case what will happen, because this weight is more than this key value, then we will do nothing and we will not do all this step. This is only happening when this value is less than this value. So let us take one graph and then we will apply these steps to understand in a better way. So move to the next. Okay, this is the algorithm. So we'll take an example and then we will apply this algorithm or these steps on that graph and see that how we can obtain the minimum spanning tree. So let us assume that the graph given to us is something like this. Let us draw here. Okay, so this is a graph given to us which consists of 6 vertices, and these are the weight edges given to us. Now we are interested to find the minimum spanning tree. So in the Prim's method, what is given here, initially for each vertex of this graph, do key u equals to infinite. So we need to set the key value for each as infinite. So, and also the predecessor of any vertex is there, means there is no predecessor is identified, means there is no previous vertex defined for any node or any vertex. Okay, so but the key value of r is 0, and q is a set that contains all the vertex. So we will assume that q is a set that contain all the vertex. So all the vertex means this is 1 2 3 4 5 6, and also these vertex are having one key values, right? So we are assuming here that our root vertex is 1, means we are starting with the vertex 1, because in the Prim's method we need to select one starting vertex. So the starting vertex key value is 0, but all of the vertex value key value is infinite. So we'll write here. So keep in mind this defines the vertex and this defines the key value. Okay. Now, while Q is not empty, we will do this. So what is required? We will do extract min Q. So this is the set which are having vertex with the key values. So we will apply extract min Q procedure. So when you apply this, what is given, it will return back this vertex 1 because these are all infinite and the minimum value is 1. Then what is required for each vertex that is adjoint of U? So you need to find the neighbors of this vertex 1. So you can write here the neighbors of this vertex 1 are, you can see from here, this is 2, 3 and 4. So 2, 3 and 4. And then you have to check if the weight of UV is less than key V, then you have to adjust the predecessor and the key value. So here you can also write the weight of 1 to 2, the weight of 1 to 3 and the weight of 1 to 4, means this edge weight. Okay, so we know that the weight of 1 to 2 is 6, the weight of 1 to 3 is 1 and the weight of 1 to 4 is 5. So because if you look at this, initially the key value of 2, now if you look at the key value of 2 is infinite, which is more than 6, the key value of 3 is infinite, which is more than 1, means all the key values are initially more. So we will take this and update the key value. So the key value is now, so key value of 2 is 6, key value of 3 is 1 and the key value of 4 is 5. We have updated, or you can also write it here so it will be visible to us. So it was let me write it as little smaller so that it will be visible in all the steps. So 0, infinite, infinite, and we have updated the key value of 2. So now this is no more infinite, this is 6 now, this is 1 now, this is 5 now. Okay, and also we have to update the predecessor. So now the predecessor of pi of 2 is 1. Whenever you are updating the key value, then only you are updating the predecessor. Okay, so if the key value is not updated, then the predecessor is not updated. So because we have updated the key value of all these vertex of all these neighbors, so then we have to update the predecessor also. That means actually the meaning of this statement is, that means if I want to go to 2 or 3 or 4, I need to follow this path, I need to go from 1 only. So if I want to go to 3, I should go from 1 only. So if I say the predecessor of 4 is 1, that means to reach to 4 I should only go through 1. Okay, then we will be also, you can, because later it is required the predecessor of all the vertex, so also you can, it's better if you make a table separately where you can visualize that what is the status of the predecessor node. So you can write here that this is the predecessor and this is 1, you can write it here 1, 2, 3, 4, 5, 6, and we have updated that the predecessor of 1 is of 2 is 1, predecessor of 3 is 1, predecessor of 4 is 1. This is what we have updated so far. Then because it's this entire thing is working in the while loop, so again it will go back and will see that Q is empty or not. Q is still not empty. Now this, when I say 1, this is already out of the queue. Now this is not a part of the queue, so we can just remove this. It is not a part of the queue. Now this is remaining in the queue. So still the queue is not empty, so we have to again call extract min queue. So now out of these available vertex, the minimum value is 3. So you will extract this one. So whatever you are extracting, just encircle it so that we can easily find out that this is not a part of the queue. So it will give you 3 because it has a minimum key value. If you come across that two values are minimum, then you can select any one. Now, so we need to find out who are the neighbors of this. So the neighbors of 3 are from this graph. You can see the neighbor of this graph is 1, 2, 4, 5, 6. Now 1, 2, 4, 5, 6. If now we have to, after finding the neighbors, if v is a if v belongs to q. Now if you look at this, out of all these vertex, now one is not belonging to q, so we will not work on this. So we will not consider this vertex because it's already not a part of q. It's already taken out of this q. So we have to work only for 2, 4, 5 and 6. So we'll see the status. So what is the path cost? We will write here w32, w34, w35 and w36. So you will find w2 is what? W2 and w32 is 5, 34 is 5 and 35 is 6 and 36 is 4. Now you have to check what is the key value of 2. The key value of 2 is 6 and this is 5. So this is better. This is 6 and this is 5. So you have to update this from 6 to 5. So whenever you find a lesser value, then you have to update, and because you are updating here, so you have to write the key of 2 is 5. Now the key value of 4 is 5 here and this is also 5, so there is no need to update anything. We will not consider this. The key value of 5 is 6 here and it is infinite, so we are going to update this and we will write here 6, and we are also updating here the key of 5 is 6, and for 6 also we will update because it's infinite here. We will take this also and we'll write here the key of 6 is 4. So we have updated these three keys, and because we updated three keys, we have to also update their predecessor. So now the predecessor of 2 is 3, predecessor of 5 is 3, predecessor of 6 is 3, and you can see here. So we have updated the predecessor of 2 is 3, so we have updated this. Now it is 3. Now earlier we have chosen 1, but now we are saying the predecessor of 2 is 3, means 3 will be giving you a better choice than 1. Predecessor of 5 is 3, so we'll write here of 5 is 3, and the predecessor of 6 is 3. Okay, so this is what we have got so far. Now let us move to the next part. Again we will do the extract min. We will keep on doing this process until we did first time, this first iteration, then second iteration, then we are doing the third iteration, extract min queue, and you have to see among the available vertex which has a minimum key value. So if you look here, the minimum key value is a 6 here, so we will take this out and we will find the neighbors of this vertex 6. So neighbors of this vertex 6 is this. So we have 3, 4 and 5. So you can write here 3, 4 and 5, but again you can see that 3 is not a part of queue, so we will not work on this. We will work on this 4 and 5. So you will find what is the cost of 6 to 4 and the edge cost of 6 to 5. So 6 to 4 is what? 6 to 4 is 2 and 6 to 5 is 6. So you can see that Here the key value of 4 is 5 and this will give you 2, so we will update this. So now this is no more 5, we will make it 2, and we will also update this. So we will write here the key of 4 is 2 now, and here you can see the key value of 5 is what, 6 here, and this is 6 here. We are not going to improve because this value is not less, so we will not take this into consideration, and we will simply move forward. So here we can write phi of 4 is equals to 6. So here we have updated this, we will make it 6 here. Okay, so we will move to the next. Then again we will do extract min q, and it will return. Now out of the remaining vertices we have to look for the minimum key. This is the minimum key, so we will get 4, and you will find the neighbors of this vertex 4. Neighbors of this vertex is 1, 3 and 6. 1, 3 and 6. Now if you look at this, 1, 3 and 6 is not a part of Q, so we will again skip this part. There is nothing to do, and you will move to the next part. We will do extract min. Extract min Q, and you will look here that out of the remaining vertex, so we have remaining with 2 and 5, and out of these 2 this is minimum, so we will take this 2 and we will look to the neighbors of 2. So neighbors of 2 are 1, 3 and 5. 1, 3 and 5. Now you can see here that 1 is not a part of this Q set, 3 is not a part of this Q set, 5 is a part of Q set, so we'll work for this 5 vertex. So we will find what is the weight from 2 to 5. 2 to 5 is 3. So we will see what is the key value of 5. The key value of 5 is 6 and this is 3. So we are going to update this. This becomes 3. And because we have updated, so we have to also update the predecessor of this 5, which is 2. So you can see here, now we have updated the predecessor of this 5 is 2. So whenever you update any key value, then also you have to update the predecessor of that vertex. Now we will go to next, extract min q, and now if you look at this, we have only left with vertex 5, so 5 will be here, and you'll find the uh, neighbors of this 5, and neighbors of the 5 is 2, 3 and 6. 2, 3 and 6, but you will find that 2, 3 and 6 is not a part of the queue, so we will not process any of the vertex further, and now if you go back and the queue becomes empty and we have to stop. So at this point you will stop and we already get our answer. So how to find that what is our answer? So here you can see that the answer can be find out by looking at this path. So final solution we can find out by constructing our final tree by using this. So let us uh, conclude or summarize this. What you will get, this is our root vertex, starting vertex, and we will write the last value. So this is the last is 3, here the last is 1, here the last is 6, here this is 2, and this is 3. So now, so from 1 you can go to 3. So from 1 you can go to 3. This is the one vertex we have chosen, and then from 3 we can so we have chosen this, from 1 we can go to 3, and from 3 we can go to 6. So from 3 we can go to 6, and also from 3 we can go to 2. These are the vertex. From 3 we can go to 2, and from 2 we can go to 5. From 2 we can go to 5, and from 6 you can go to 4, and we will write the cost of here. So we know that the cost of this is 2, or you can write from here that here we have 2, and then we have 3 to 6 is 4, and 1 to 3 is 1, and 2 to 3 is 5, and 2 to 5 is 3. So the minimum spanning tree, this is the minimum spanning tree that actually contains all the vertex of the given graph, and the cost, if you find out the cost, this will be 3 plus 5, 3 plus 5 plus 1 plus 4 plus 2, and this will be what? This will be 8, 9, and 6, 15. So you will get your minimum spanning tree, and the cost of this tree. When I say cost, cost means the weight of all the edges that connects to this vertex, to all the vertex. This is 15. Now there's a possibility that you may get different structure of this minimum spanning tree, but the value will always be the same. Now why we get different structures? It is possible because while extracting the minimum value, there may be a possibility that while extracting you may get two vertex with a minimum key value. Then you can pick any of them. So while picking these different vertex will may give you a different structure, but the final cost of the minimum spanning tree will always be the same. So this is how we can construct a minimum spanning tree, and in the later video we will be going to analyze its running time. We will see that what is the cost of uh, constructing the minimum spanning tree, and also we'll compare the cost of constructing by using a Prim's method and also by constructing using a Kruskal method. And one more thing, the cost you can also find out by looking to the key values of the vertex. So we have find the key values here. So in order to find out the cost of this minimum spanning tree, you simply add all these values. So this 5 plus 1 6 plus 2 8 plus 2 11 and plus 4 15. So this is also one way of directly calculating the cost, and this is using this table we can construct our spanning tree, minimum spanning tree. So this is all for this lecture, and in the another lecture we are going to talk more about this minimum spanning tree. Thank you very much.